and C basics. We're looking at this program that converts kilometers or miles to kilometers, excuse me, and we're going through the anatomy of a program one by one and looking at each one of those aspects of it, including the comments, which tell the why and the how, not necessarily the what, because code should be self-documenting. We looked at preprocessor directives to make your life easier, to bring in external libraries so you don't have to start from scratch, and to define aliases so that you don't have to use magic numbers. We also looked at the other major aspects of things. For example, generally white space doesn't matter, but things should be indented and should be indented nicely at the same level. Commas, semicolons, and other punctuation are used throughout, just much like they are in English, to denote sentences, paragraphs, and other aspects that have a parallel with regular Old English. All right. So what I want to do now is move on to the next part, the actual functionality of this program, input and output. Right? So take a look at this program and tell me what's responsible for output. What's responsible for printing something to the screen, to the terminal down here? Printf, exactly, right? So when we say input and output, right? Output in C can be done using Printf, right? It stands for print formatted. Right? That's what the F stands for. And there is no formatting here with this first print because you just want to print a regular old message. But if you want to format actual variable values for a human readable output, right? Remember, a computer is just a bunch of zeros and ones. So all it knows is 0, 1, 0, 1. High voltage, low voltage, vacuum tube, compressed, not compressed, whatever, right? But if you actually want to format it so that somebody can, it's base 10 and human readable, you need to use what are called placeholders, %F and %F. Now we're using two floating point numbers here, miles and kilometers, because we want to support the idea of you can convert 10.5 miles to whatever kilometers that happens to be. So it stands for print formatted, in which you can print variable values using what are called placeholders. Now the placeholder that we just, nope, that should be look like that. All right, fine. The placeholders for integers, right, use %F for floating point numbers, right? That is fractional numbers, such as 10.5, 3.14, even negative values, negative 10.2, or even whole numbers that you want to print the actual fractional value out of 0.0, right? Use %D for integers, that is whole numbers, positive, negative, and 0. And you can use %C for single characters. This is a preview of the types of variables that we'll be taking a look at today. These three. There are more variables, but we're going to keep it simple, and we're going to only look at these three. %F is for floating point numbers. That kind of makes sense because you're using F. But we're only going to introduce the idea of doubles in this course. So why isn't it %D? Well, %D is reserved for integers. Well, why isn't that %I for integers, right? Reasons, right? I didn't write it. Somebody else, %I has a different meaning, reserved meaning already. And so they had to use something else. D is short for decimal, or digit, I think, right? %C is really the only one that makes sense. If you want to print a single character, character starts with C, and that's what you use, right? Now let's go back to the actual code here. Anytime you see one of these placeholders, it'll be replaced by whatever value is stored in the variable that you provide after that formatting string. This double quote, that's called a string. Anything that you put inside of that will be printed, right? And the % signs here, the placeholders will end up being replaced by whatever value is stored in miles and whatever value is stored in KMS. Right? If you have multiple placeholders, right, then the first variable corresponds to the first placeholder. The second variable corresponds to the third one. If you provide 3 placeholders but only 2 variables, you can do that, but the compiler will complain. GCC, miles to kilometers. And it will warn you about it. Warning, %f expects a matching, right? The argument of double, but we didn't get one. There's 1, 2, 3 placeholders here, but there's only 2 variables. If you have 2 placeholders and only 1 variable, again, the compiler will complain about that. And it'll expect that there should be 2 variables here. Right? Note, however, that it's only a warning. All right? It's not an error. It will still compile, it'll still run, it'll just give you the wrong results. Right? It's just warning you that this is probably something that you want to address and fix. Right? There are plenty of things that are warnings that you can still get away with, but you can't expect your program to actually operate the way that you intend. Right? Only syntax errors are actual errors. If you forget a semicolon somewhere, then it won't let you compile at all. Right? Then it's actually a full error, and you can tell that by the red there. Right? Error, expected a semicolon at the end of line 17, at character 35. Right? So read your compiler, even though it can be cryptic at times, and you don't necessarily know what the error message is, you at least know that there's an issue in or around that line number that you need to address. Okay? Now there's also another placeholder here if you're really steely-eyed, %lf, right? That's for scanf, right? So if output is done with printf, input in C can be done using scanf. Now I say can be because there are other ways of doing this stuff, but these are the 2 that we're going to cover up front here, right? When using scanf, use the same placeholders, except when reading in a double value, right? Then use %lf. Instead of %f, use %lf. You might be able to get away with %lf on printf too. It's entirely system dependent, I believe, and so I caution you and just remember these rules, right? That if it's scanf, you need to use a %lf. Oh, right? Another caveat, another thing, gotcha, right? When using scanf, to specify the variable you want to read into, you place an ampersand. And the ampersand looks like that. In case you're not seeing it on your keyboard, it's the Shift 7 button, right? The ampersand in front of it. For now, reasons, right? I don't want to get into it, but basically the ampersand gives you the memory address of that variable so it can be passed by reference when you call a function instead of passed by value, so you can actually make changes to it. Put that in the back of your mind, and in 6 weeks we'll understand what I'm talking about there when we get to pointers and functions. Okay? For now, just understand that if you use scanf and you don't have that ampersand, once again, the compiler will complain about that, and oops, KMS Miles, let me fix that other error there. Just understand that the compiler will complain about it, come on, and give you a warning, right? It expects a argument of type double star, and you gave it a type double. Again, that's kind of cryptic because we don't know about pointers yet. Just understand that, oh, okay, %lf, scanf, oops, I forgot my ampersand right there. Okay? In fact, it'll even run. It's just a warning. Right? It might even work. 0.5. Nope, it doesn't. Good. I'm glad it doesn't work. Right? Good. All right. Any questions so far? No? All right. Then let's talk about those 3 variables that I was just talking about. Integers. Oh, sorry. Where? Sorry. Go ahead. Oh. There you go. Well, also the ugly yellow is hard to see, making it hard to see too. I don't know if that's part of the projector or like somebody actually. It's probably the projectors going out there. I'll try to put in a ticket for that, but replacing a projector is probably a no. Maybe replacing the bulb even is probably a no. Going up there and wiping it and seeing if that works, I imagine that's doable, right? All right. So C is a statically typed language. Don't worry about the technical details of what statically typed means. That basically just means, you need to declare a variable before you can use it. Declaring a variable means specifying its type and its name. Another name for name is identifier, right? Name is a little bit more understandable though, so I'll stick with that. Let's come back over here to our program and see what kind of variables we have. First of all, why is a variable called a variable? Think about basic algebra, right? Why do you call x a variable? It's a letter instead of a number, but it can change, it can vary. That's why we call it a variable, right? It can change its value, right? Here's the number line, x, right? It can be 0, it could be 5, or -5, it could be +5, right? And as it varies on the x-axis, then the value of your function that you're trying to graph changes as well, right? What's the opposite of a variable? Something that doesn't change. Constant, exactly, right? And you can think of KMS per mile as a constant. It's not really a constant in C, but it's basically achieving the same thing. Somebody can come up here and change it to something else, right? But in the codes elsewhere, they can't change it. And if you can't change it, it ain't a variable. It is a constant, okay? So what kind of variables do we have here? A double, and I've got multiple ones. If I've got multiple things in English, list of cake, ice cream, and cookies, right? Comma, comma, comma. And I can do that with variables too. I could have put that on 2 lines, right? Why write 2 lines when 1 line does well, right? Comma, there we go. I declared them, meaning that I said, hey, up front, there's this variable called miles, comma, there's this variable called KMS. What type are they? They are type double. If I change that to an integer is a whole number, 10, 5, -5, 0, right? Would I have been able to support somebody entering in, I want to convert 10.5 miles over to kilometers? No. I'm making a design decision here to force you to only consider whole numbers. And some things are only whole numbers. For example, the number of students in this class, right? I think we're at 160, right? Or something like that. A number of students is an integer, right? There's no such thing as 1/3 of a student, right? So your variable choice matters. You need to make sure that they're the correct type, right? And you need to make sure that you're declaring them before you use them. If I attempted to use a variable up here, right? Printf, miles is equal to %d and the line, miles, right? If I attempt to use that variable before it exists, do you think that this is going to compile? Probably not. In fact, it says, oops, I never restored my ampersand. Make sure to do that here. But there, it's a full-on error, right? Undeclared miles. Think about, put yourself in the mind of a dumb computer, right? You're parsing this out. You're compiling this program. You get down to line 14. Have you seen miles yet? Nope. Miles is declared down on line 16, right? But you're trying to use it. I don't know what the heck you're talking about. Miles doesn't exist yet, right? You have to declare it before you use it. Not only that, but it has a scope, right? So now we'll understand this a little bit better when we actually get to more complex code. But the variables miles and KMS, they only exist in this main function right here, right? Because I declared them up here, and they're within this code block that begins with this opening curly bracket on line 12 and ends with this closing curly bracket on line 26. That's its home. That's the only place that it exists. As this is computing, as this program is running, and we execute this print command, execute the scanf command, execute, 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 when we get to the end of that block, those variables go out of scope and they no longer exist, right? Why do we call it scoping? Well, if you just keep your eyes open, you can see the entire world, right? The things that are viewable. But if you look through binoculars or a periscope in a submarine or something like that, Your vision is limited. It's limited to only the things that you point the scope at. Right? So if there's this variable that exists over there in one function, and I'm in another function right here looking through my scope, do I see that variable? Nope. I can't use that variable. I can't change that variable. I can't do anything to that variable. Right? I only see what is immediately in front of me in the current code block. Okay? So that's what we mean by scope. You're declaring a variable means that you specify its type and its name. A variable only exists within the block of code in which you declare it. Right? Otherwise, this is known as the variable's scope. Right? If it's out of scope, then it's out of scope. You can't see it. You can't use it. You can't do anything with it. Okay. What about types? Right. So we already gave a preview of this. There are 3 types: an int, a double, and a char. Right. So you could call it char, but since it's shortened up and it's not character, you could call it char. That would be conformant to character, but it's char, so char. Yeah. Don't do that. You can have inner functions, but I don't cover that. I don't show that. But you can have inner blocks, right? So for example, I could have another opening curly bracket. And within that, I declared those 2 things, and another closing curly bracket. Now where is the home of those 2 variables? Between lines 14 and 16. This will not compile. It was declared right here within these 2 things, and it does not exist after those 2. So this will not compile either, I hope. Right? Yeah, good. Miles is undeclared. KMS is undeclared. I don't know anything about them. They were born here. They died here on line 16. Right? Yeah.
If you declare for that new code block, can you use it within the new code block?
Yes, you can. For example, you could print miles here, printf, printf miles is equal to %d and the line miles. It still will only complain about the other lines of code.
If you move double miles KMS to line 13.
Oh, yes. Yes, that will work. Now everything works. Right. Okay. Good. So that's scoping, and here are my 3 types. Others? I need to increase my scope, so I'm getting whiplash trying to go back and forth. So please, everybody just raise your hands and point like you did before. Yeah?
So you could use those, if you wanted to define a variable, you use one of those 3 things, right? What's the hashtag define KMS different?
Remember that was the preprocessor directive, right? That's not a variable, right? Because you can't change it, right? I mean, you can change it by changing this stuff up here, but within the program itself, you can't change it because it's been replaced by the preprocessor before it even compiles.
So what would you say the benefit of making it? Because you could also make that a variable, right?
You could. Okay. So here's a way that you can. Here's the best way that you can make that variable. I didn't want to get it. Don't necessarily do this, but const. Actually, no. Let's do it this way. Double KMS per mile is equal to 1.60934. There's an alternative, right? Now that is a variable, but what's the problem with a variable? It can vary, right? What if you did this with pi? Now somebody can change pi to 4, right, in their program, and break it for all the other code that relies on the fact that pi is well defined, right? The better way of doing that is to make it into a const. What do you think const is short for? Constant, right? And now nobody can change it.
So the benefit is just if you don't want it to ever change, and then if you have like a really long program.
Yeah, to use a preprocessor directive or a constant global variable, which is best? There are arguments for each and use cases for each. You might not want to use a variable because then that's taking up memory, right? Yeah, it's only taking up like 8 bytes of memory, but it's still taking up memory. Whereas you could have probably taken care of that even before you compiled and gotten rid of that variable entirely. So I'm going to go ahead and comment this out, right? What's the quick key for commenting something out? Right? Command / Windows users, I believe it's going to be control / Right? There we go. All right. So an integer, what are integers? Is a whole number. Both it can be positive or negative or 0, right? But with a limited range, right? And this is because this is how numbers are represented in a computer. A computer is not an infinite object, right? Imagine if it were. You would never have to upgrade your RAM ever again, right? You are limited to 8 gigabytes of RAM if you paid for 8 gigabytes of RAM, right? Gigabytes of RAM. An integer, likewise, is limited. It can't just take as much space as it wants. And so it's actually limited to 32 bits. A bit is a 0 or a 1. And so consequently, it is limited in the type of number or the range of numbers that it can represent. Right? Typically, with a 32-bit signed 2's complement integer, details, forget about that. Just know that you can only represent numbers in that range right there. Now squint really hard and put commas between that and tell me how big is that number on the right. Is that millions, billions, trillions, what? It's billions. 2.147 billion, right? So there's 3, there's 3, there's 3, and then we have a 2. 2.147 billion and change. Likewise, negative values. You can express at most negative 2.147 billion. What happens if you try to represent values other than that? Let's come over here. Int foo. Foo is just a placeholder value. Otherwise, sometimes we use bar, baz, right? Foo, I'll set that equal to that upper end, right? There we go. And here's a bit of a preview of some math stuff here. Foo is equal to foo plus 1, right? Now, when I get up to that maximum value and I add 1, is that representable according to this equation right here? Nope. So I wonder what happens. Let's go ahead and print it out. Printf. Foo is equal to %d, and foo. Right. There we go. Run it, and we won't worry about the interactive input down here, input-output down there. Foo. Does that number look familiar? Negative 2.147 billion and change, ending with a 48. There it is, right? So numbers don't work like they work in math in a computer. Let's put on our math hats and think about how numbers work on the number line. We start, here's the x-axis. We start at 0. Negative values go off that way, positive values go off that way. Do they end? Nope, it's an infinite line. Computers are not infinite objects, they're finite. We can't represent arbitrarily large or arbitrarily small numbers. So we have to have a cutoff point. The cutoff point down here is negative 2.147 billion. The cutoff point over here is positive 2.147 billion. And now it's not even a line. Think of it like a circle. Right? I'm going to take this line and wrap it around on itself. Right? I'm going to start at 0 and start adding things, 10, 20, 30, 40, 50, 60, and go all the way to the largest value that I can represent, 2.147 billion, blah, 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 47. And now add 1. Where do I end up going? Back towards 0 at the top on the negative side. Right? And that's where I end up. It's called overflow. Take a glass of water, or just a glass, an empty water, and then start pouring water into it. It gets up to the top and it's full. Can you add any more water? You can, but what happens? It overflows. Right? That's what happens when you fill up the available amount of memory and you're only limited to 32 bits. You start adding more, right? And it overflows. And where does it go? It goes around in that circle onto the negative side. What do you think happens if you try to go from 0 and subtract 10? So negative 10, negative 20, negative 30, negative 40, right? And then you get all the way to the minimum value, the minimum value that you can represent. And then you go into the positive range, right? And you end up on the other side of that circle, right? And that's how overflow works with an integer. If you want to represent something larger, you can. You just need to bring in a library to do it. Right? What about doubles? Doubles are floating point numbers. They're fractional values, right? They're floating point numbers that have a fractional representation where you can represent up to 16 digits of accuracy. 16 digits of accuracy. It doesn't matter if those digits are way over here because it's a huge number. It doesn't matter if it's 3.14159 pi out to 17 digits, right? It's just 16 to 17 digits, period, right? Did we do this last time with the 1/3 trick? Maybe, maybe not. I don't know. Let's try. Let me show you what I mean by it. All right. All right. Let's create double foo, and I'm going to set it equal to 1.0 divided by 3.0. Right. What's 1 divided by 3? 3.333333. What do you do? What do you do in grade school math to indicate that it goes on forever? You put a little bar above it, right? That means that it's a rational number, and 333 repeats forever. Right? Let's print it out. Foo is equal to %f and the line foo. Kill this. There we go. Right. 0.333333. That's because by default, we're only printing 6 decimals of accuracy. As a preview of what we're going to do maybe on Monday, let's print out more digits of accuracy. 10 digits of accuracy. Yep. I'm going to take the rest of this and get rid of it so we don't have to deal with it anymore. There we go. But I'm preserving it so that when I copy it to the notes, you'll still have it. 0.333333. If I only have 17 digits of accuracy, I would expect those 3s to go out to about 17 digits of accuracy, and then what happens after? Yeah, let's find out. 1483. It's garbage, right? Those are just random numbers. Not so random, but those are system-dependent numbers, right? It only goes out to about 17 digits of accuracy. Now, you can multiply it by 100 billion, right? And make it really, really huge, way bigger than 2.147 billion, but you'll still only get 16 digits, significant figures on the most significant end, right? I can multiply it by a lot, right? Let's go. Foo is equal to foo times 1 million. Do that again and again and again. Very, very large, right? And it won't overflow. It'll just say that it's very, very large, right? Maybe that's too much, but I don't know. Is that right? I think that's right. Fine. More. It'll probably print out scientific notation at that point. Nope, it doesn't. Right? So it's very, very large, but you'll note you only have 17 digits of accuracy, or roughly 17 digits of accuracy over here. What's the rest of it? Garbage, right? It should be 33333 off into infinity, but it isn't, right? So understand the limitations of all these numbers. That's what you'll do in your lab next week. We've prepared several programs so that you can find out why is like what values can actually be represented, what values cannot be represented, right? What about a char? Is a single character value, right? From the Ascii text table. Did we look at the text table, the Ascii text table? Okay, good. AsciiTable.com. Right? So if you go to AsciiTable.com, you'll find out what it stands for. It's the American Standard for Information Interchange. And the reason it's the American standard is because it was developed in the Eisenhower administration, right? Right after World War II or something. And it's because they had these QWERTY keyboards, right? They had QWERTY typewriters back then. The QWERTY keyboard layout, right? It predates modern computers by 100 years or so, right? And so they were thinking, okay, well, when we've got these new electronic typewriters and electronic things, we're going to still need to type stuff in. So we need to come up with a standard that encapsulates all of the keys that you see on your keyboard. Right? And since it was developed by America, it was very America-centric, right? And you had A through Z in order. Who would have thought? You have lowercase a through Z in order. You have all the punctuation that you can find on your QWERTY keyboard on your old school typewriters, right? You also have other things. For example, well, how do I backspace? Right? Well, that's value number 8. How do I go on to the next line? Line feed. That's ASCII value number 10. Each one of these things has a value. Capital A is associated with 65. Lowercase p is associated with 112. And in total, there are 128 of them. We start at 0, so the last one is 127. It's the delete key, right? There is a difference between backspace and delete, right, on keyboards. We also have a bunch of unprintable characters here. For example, ASCII text value number 7 is a bell. Right? You can make your computer go bing, right, by printing that character. Right? You can intentionally write a program that goes into an infinite loop, and every time it executes that loop, it does a bell, right? So ding, 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 forever and ever and ever. Right? You can make music, right? You don't want to do that. So they realized that, well, you know, other countries and with different type systems, they have other characters, right? Right? So they extended it eventually to the extended ASCII text values, right? And these are supported by C, but it includes like umlauts, right? With diacritics and things above each one of those characters, the carets and the accents and stuff like that. Well, that wasn't enough. Eventually, they came up with an even larger standard called Unicode. Right? Unicode has room for millions and millions of characters instead of just 128 of them, or 256, including things that maybe should not have been developed. Emojis, right? Emojis are Unicode characters that are supported by most modern devices. You can use them, but you shouldn't be using them in your code, all right? Anyway, it has a number, right? Just like uppercase A is associated with the value 65, this grinning smile face emoji is associated with this much larger number that's represented in hexadecimal here, right? You can get pretty much any character font system that you want, CJK fonts, Chinese, Japanese, Korean fonts. You can get ancient Egyptian hieroglyphics in Unicode. You could type out ancient Egyptian hieroglyphics. Right? The one thing that they accepted emojis, and that's growing. The one thing that they rejected was Klingon. So, yeah, so you're going to allow emojis and smiley faces, but you're not going to allow a fake language? Whatever. Right? So I don't know. Are there characters for Pig Latin? I don't know. You can make up your own Unicode and then propose it. You just have to go through the official process. I don't know how long it takes, but one guy documented the way that he did that, because Unicode has stars, right, and then filled stars. So for rating systems, instead of printing out graphics that you get 3.5 stars, you can use Unicode, which is much smaller and more compact. The one thing they didn't do was have half stars. So he came up with a proposal to, let's add that half filled in star to the standard, and they said, yeah, okay, we'll go ahead and do that, right? He just had to go through the process of doing so. Right? And then he documented and made a blog post about it. You could probably look it up. I don't know where it is. Right? There are others, right? Sorry. Look them up your own. There's float. There are Booleans if you bring in a library, if you're familiar with Booleans. That's what I'm going to limit my presentation to, though. I'm going to keep it simple. Right? That is a nice acronym in engineering. KISS. K-I-S-S. What does it stand for? Keep it simple, stupid, right? Don't do it. Or it should be keep it stupid simple, right? That's much kinder, right? Anyway, keep it simple. Variable naming, I should say. Naming, right? So generally, you should use lower camel casing for a convention for your variables. Right? So note what I did there. Lower camel casing. If it's multiple words, the first word is all lowercase. Every word after that, the first letter is uppercase, and the remaining letters are lowercase. Okay? That's why we call it lower camel casing. The first, why do we call it camel casing, first of all? Think about a camel. What does a camel look like? Humps, right? The two-hump camel versus the one-hump camel. I have no idea what the difference is. But it looks like a camel, right? Because there are a bunch of humps in there. It lends itself to very, very readable variable names. So for all of your variables, you should be using lower camel casing. For all of your functions, eventually, when we get into that, use lower camel casing. There are other conventions. For example, one that we've already seen. Upper underscore casing, in which all the letters are all uppercase, and you separate the words using an underscore. Right? So one other convention would be upper underscore casing. Those things down at the bottom are called underscores. You can also have lower underscore casing. Right? Why might you want to limit both of those? Well, first of all, why would you want to limit the number of times you use all caps? Yeah. Yeah, you're going back to the caps lock, or you're holding down the shift button the entire time that you type, right? And good luck with that. Right? Why might you want to avoid underscores entirely? Yeah. They blend in. It is not visually appealing, right? But also, think about your poor fingers. What are you doing every single time you type an underscore? Shift, yeah, and then you've got arthritis in your little pinky. And then also, you go all the way across the keyboard to the hyphen to get the underscore, right? Anytime, I mean, the QWERTY keyboard has a layout that it has so that that you can type fast, right? Underscores necessarily force you to type slower, right? So save your pinky, increase your typing skills, and go with my suggestion here of using lower camel casing. Right? It really doesn't matter. If you want to go with a lower underscore casing, you're going old school C, fine, go ahead, that retro look. But just be consistent about it. Right? Don't use lower camel casing in one part for one variable, and then lower underscore casing in a different part for another variable. Upper underscore casing is generally used for macros and constants, right? Like, for example, m underscore pi in the math library, right? They're figuring that, well, it's short enough, it's infrequent enough, it's okay that you use it like that, okay? In general, the reason that we need these conventions is that no white space is allowed in variable names, right? Variable names must begin with a letter, right? They can begin with an underscore. Don't do that. That's a different convention, right? But I don't want to make myself a liar by saying that you can't do it. They may contain numbers and letters, right? But again, no white space. Right? I say may because it's probably a bad idea to use numbers in your variable names, because then you get into the bad habit of my variable 001, my variable 002, my variable, I need a third one, my variable 003. Those are all terrible. They're terrible names, right? Good variable names are descriptive, right? They describe what the variable is modeling, right? For example, number of students. I'm using lower camel casing convention there, great. And I'm using a very descriptive variable name, number of students. What about, or miles, right? We also use KMS. Is that a good variable name or not? No? Okay, why? I had no idea. Okay. What about if you had a different variable name called SSN? Do we know what that is? Social Security number, right? but that's because we're, at least the majority of us here are Americans, and we all have social security numbers or tax ID numbers, right? What's an NUID? Nebraska University ID. You go over to Iowa, do you think that and you used in your code NUID, you think that they're going to know what the hell you're talking about? Right? Go over to Dublin, do you think they're going to know what you're talking about? Right? No, not at all, right? So sometimes you can use abbreviations and acronyms and stuff like that, and if the context is absolutely clear, you are good to go. The question is whether or not the context here is absolutely clear. I'm coupling it with miles and KMS. You'd have maybe a 60, 70% argument that, yeah, it's absolutely clear. If it isn't absolutely clear, then don't do that and go with a better variable naming convention of a full thing. You're not getting paid by, and you are not paying by the character. You might as well write the entire thing out, right? Unless you're the world's worst typist and K-I-L-O, right? Kilometers, right? Just practice. Right? So, baby, or maybe some other things. APR, what would that be? What? Annual percentage rate, right? Now, if you've never been exposed to finance before, then you wouldn't know what that is. SSN, right? If you're not an American, then you wouldn't know what that is, maybe, right? NUID, etc. These are all questionable. What is absolutely bad, though, are variable names like, say, my variable, right? Or var001, right? Or A, B, C, right? Or sometimes X, Y. Right? Yeah. Now, I'm calling out the entire world of math here because that's what math does, right? But when you're in your calc class and you are graphing x squared, the derivative of x squared, right? And you have x and y. Do you have anything that represents x and y? No, you're talking about it in completely abstract terms. Yeah.
X and Y might have exceptions if you're making like a video game because the X and Y.
Yeah, we're going there in a second here. Where if you are just talking about something in the Euclidean plane, sure, go ahead. But if you've got like any other graph, right? Like money versus time, do you call them X and Y then? No, you label them as money and time, right? Otherwise, if it was X and Y and you gave me this graph, what is this representing, right? You're completely lost. X and Y and A and B and C are okay variable names when you don't know what it's necessarily modeling. Or you've got an application where you're talking about X and Y distances. I've got X1, Y1, and I've got X2, Y2. I've just got points in the Euclidean plane, and I want to compute the distance between them using Pythagoras' theorem or something like that, right? Then, yeah, it's not representing anything in particular. Go ahead and use X and Y, because that's the best you can do, what you should, in general, right? What you definitely should not do is, X1, Y1, X2, Y2. Don't just go X, X, and I need another one, Y, Y, right? You're going down the wrong path. Another exception that we'll get to later on is loops. And when you use an index variable and you use I, J, K, idiomatically, that's okay, right? Now, what do I mean by idiomatically? Well, what's an idiom in plain old English? It's raining cats and dogs is the perfect example, right? That's what the example I was going to use too, right? It's a colloquial metaphor. If I literally said raining cats and dogs, right? There's a meaning there that is well understood among people that understand that native language, right? That it means it's raining a lot, right? It's not has it have its literal meaning of it's raining cats and dogs. That's an idiom, right? And it's particular to a particular language and even to a particular culture. If you took raining cats and dogs and you translated it to Spanish or Japanese or Chinese or something like that, it would make no sense at all, right? They would have their own idioms, and I don't know any of them, right? So I can't say. Right? Actually, I do know a couple. In Japanese, asameshimae. So before breakfast. I just literally translated that. Do you understand what I mean? Right? I would translate that as piece of cake. Now do you know what I meant, right? Easy, right? And so those are idioms. In code world, in the code world, we have our own idioms. We have things that everybody understands what they're doing because they've been exposed to it and they have a lot of experience with it, right? Once you see those patterns over and over and over again, they become idiomatic. They become just muscle reflex. And when you've got I, J, and K, that automatically speaks to me. You're talking about loops there. You're talking about index variables, right? In that context, it's okay. But generally, just A, B, C, D, E, F, G, H, I, J, K, L. No, those are terrible variable names. Don't do it, right? Let's see. Really quick here, and with only 5 minutes, I will give you the simplest operators that we have in this programming language because you probably already understand or grok what they are. There's another good word. I'm throwing a lot of jargon at you. It's okay if none of it sticks because it's all just slang anyway, right? Grok, G-R-O-K. It's from old sci-fi book, Stranger in a Strange Land by, not Allison. Help me out. Anybody? Heinlein, there we go. It's our Heinlein book. And grok means to understand something intuitively and without even thinking about it, right? At this point in your academic careers, you understand the first two without even thinking about it. If I write plus, which is on the QWERTY keyboard, I mean addition. If I write hyphen, which is on the QWERTY keyboard as well, that means subtraction. Now, the other two are not necessarily automatic, but do you have that X sign? Well, you have X, right? You have X on your keyboard, and that looks like times, but that's not what we use in code. Instead, look at your QWERTY keyboard and come up, well, what kind of looks like that multiplication? And when I say multiplication, right, I mean this thing. That thing right there, right? When I say division, I mean this thing right here. Is that gonna, yep, there we go. The horizontal line with the 2 dots, right? Are either one of those things on your QWERTY keyboard? Nope, because the QWERTY keyboard is 200 years old, right? They weren't thinking about typing out math back then, right? So what do we use in place of it? A star, an asterisk, and is that a forward slash or a backslash? That's a forward slash because you're leaning forward, right? That's division. A divided by B, right? Any questions on that? Otherwise, again, where did we use it? Now we should be able to grok this entire thing, understand this entire thing. You prompt the user for input. You read it and place the value into this variable here called miles. Then you compute KMS per miles times miles. And here's something that we haven't covered that we'll pick up on Monday, an assignment operator. We're taking the thing on the right-hand side and putting it onto the thing on the left-hand side. And then we're printing it out, right? So one thing remains here to understand this basic I/O program before we move on to more complex stuff, right? And then a couple of gotchas and stuff like that. Otherwise, that's where we'll pick it up on Monday.